Hello everybody, so today I will talk about the system design of Uber, and this is my second part of the Uber videos, and this is the part 2. So I actually took the same video yesterday, but I want to do this for my practice sake. Okay, so today I will talk about two topics. So matching process. So how the user, after user makes the request, how the driver is matched to the request. I will talk about that. And also, as I said, I will talk about the strong consistency of the matching. So user should always match with single driver. Um, the double matching should not be accepted as a system. So I will talk about that too. And then I will talk about the geospatial search. So this is a kind of process in the matching process, but I will dive deep into how I can do the optimization of the geospatial searches. Okay, so that being said, let me get started. Okay, so I will talk about the matching process. So for matching process, I wrote like this in the specification, which is the function requirement. So user requests a ride and drivers are notified on the ride request with push notifications, and the first one can accept the ride, and then with this, user matches the driver. And as the non-function requirement, sorry, this one, no, this one, we need the strong consistency of matching. And so in my current design, it happens with this request worker. So from the change data capture of the request table, this request worker knows which request is newly created, and it has to find the drivers for the request. So what it does is, firstly, this makes the query to the, of course, user table and driver table. Sorry, I've just updated the, database here. I added user table and driver table, which were missing. So because user table has a longitude latitude pair and driver table too, so this request worker can know where the requested user currently located, and then from his location, it filters out the drivers nearby. And then this request worker sends a push notification to the through the notification service, and then now driver receives it. Now driver makes a response if he'd like to accept the ride or rejects the ride, and this is sent to the, this hits the answer request API, and it creates the driver response record, and if it's a matching, where it should say accept, if the driver accepted, it creates the match recode too, and of course it does, update the request status to matched as well. So that's the kind of process I clarified in my first video. But I can say there are some problems. So number one, with this design, so in the driver's side, maybe he sent so many requests. So let's say there was a concert in the stadium, and after that, there are so many users who will request the ride. And in that case, if the push notification for the request is sent to all the drivers nearby, it means that the driver receives so many requests from the users nearby. This is a bad user experience for driver. And also another problem is that, also because there are so many drivers who are competing. Okay, this happens in the opposite case. Let's say there are many drivers and there are less users who request a ride. In that case, many drivers compete for getting the match for the same user, which means that there are many users who accept the ride, but after that, because of the, aside from the first driver, there, even though he accepted the ride, he doesn't match. So it's a quite bad experience for driver. So I have to think from the function requirement. So what is the best process for this? So, okay. So I can say there are two things I'd like to, satisfy. Number one, driver is sent up to one request at the same time. So driver can see only one request. And another thing is, because, to avoid the problem, driver accept but doesn't match issue, the one user, the chance to match with the user is given to only one driver. So there's always not multiple drivers. The situations that multiple drivers compete for the single user should not occur. So I will write it down here. So driver should, okay. And one request. Wait a minute. So, okay, a request is notified to up to one driver at a time. A driver should receive up to one request at a time. Yes. Okay. So I clarified the function requirements in detail. So I will think how I can achieve this with strong consistency. So in a naive way, what I can do is request worker should look for, the drivers, because we have the 1 minute. The system has 1 minute to find the matching for request. It can try maybe 10 times with each 5 seconds of waiting time. Oh, sorry, I actually didn't say this. I didn't say this. So in the system, the driver, in this way, the driver is given a chance to match, and he has to quickly answer if he'd like to accept or not, to make the cycle quicker. So let's say a driver is given only 5 seconds to match or reject. Okay. So I will also include this in the function requirement. So in this way, this request worker requests the driver up to 10 times with some buffer to the 5 seconds. So this request worker firstly tries the first driver and sends a push notification. And after 5 seconds, if he accepted it, this request worker now finishes to find the match for that user, what should I say, that request. But if this user doesn't accept, or if this user doesn't respond, the request worker tries to find the second candidate driver. And so he pushes the send notification. So what I mean to say is, the request worker should know which drivers are nearby the user. So it is not optimistic to make the query every time. So what I can suggest is request worker fetches the nearby drivers in one query. And let's say it gets 30 drivers with some buffer, and it stores it, it keeps it in the memory. So with this, it has to do the geolocational query only once at first. So request worker, I will write it down. So request worker makes a query to fetch 30 nearby drivers. Then check one of them, and let's say if he's occupied, or in the matching process, skip him. So with this, I can say yeah, this function requirement is now met. A request is notified to up to one driver at a time. Oh no, sorry. A driver should receive up to one request at a time. Because if he's much in the matching process, the request is not sent. But I have to take care of the strong consistency when checking this. So I will come back at this later. So now it checks one of them, and if he's not occupied and he's okay, sends a push notification to him. Yeah, so this is it. Then after 5 seconds, repeat from number 2. Oh, but here, one more thing I have to do. If the request finds a match, finish. It can finish the job. So that's something I can say. So yeah. In this way, now request worker can send a push notification to the driver who's not occupied yet and not searching currently. I mean, not in the matching process currently. Yeah. Okay. But as I said, there is a problem here in the driver's status. So I have to take care, if the driver's current status is what. So I add some status. So I can say for 3, of course, the user can be offline when he's not working, and also he's available. And also there is a status I can say kind of matching. And also I can say he's matched and driving the user. So these 4 status can be stored as the driver status: offline, available, matching, matched. So the important thing is that there are multiple request worker processes who is looking for the driver match for each user. So let's say there is a process 1 and process 2, and it is possible that because of the race condition, driver's status is read to be available for 2 processes if I don't guarantee the strong consistency somehow. And that's the problem, because now multiple processes send a push notification to the same driver. So I have to avoid this. Okay, so I will write it down. So to avoid the race condition on driver status. Okay, so I come up with some solutions. Let's say because this driver dot status column is the most important one, maybe I can use PostgreSQL isolation level serializable. Okay, so this is option number one. So this is isolation level is the configuration of the relational database. And if this is serializable, it means that each query which is sent, or I should say thrown to the database is handled a kind of one-on-one. So it kind of treat each query as if they occurred one-on-one. Sorry, one by one. So that's the isolation level serializable. But this works, but this is not efficient in terms of the performance. Because what happens is that many queries are waiting in the queue to be handled by PostgreSQL. It means that the queries which are not related to this driver status is also waiting in the same queue. It makes the performance of this relational database worse for every query. It, too much. So I don't use it. And option number two is using the raw rock. So I can say this is pessimistic rock. And also I can say as another option, I can use the optimistic concurrency controller. Yeah, so these are two options I can use more. So let me quickly tell you about the process where this race condition occurs first. So let's say there is worker process one with driver one that is available. And ordinarily, without race condition, worker one update driver one's status to matching. Yeah. And let's say there is another worker process to read, and this is now matching. So now worker to process skips it. So this is the case without race condition. But let's say there is a race condition in which firstly driver one reads the driver one status available, but now before worker process one updates the status, another process reads the driver one status as available. Yeah. So now both of the worker one and worker two thinks that driver one is available. So it updates the driver one status to matching, and this happens for worker process two. And now both of these worker processes sends a push notification. So this is the race condition. And the problem is how we can avoid it. So with the pessimistic rock, what it does is it takes the rock for this row only, which means that driver one's row in driver's table is rocked with select for update query. So the process sets a transaction and reads the driver's row with select for update query. With this select for update query, the lock of this row is acquired by process 1. So now another process, even if he tries to read it in the same way with select for update, because he has to, process 2 also has to get the lock, but the lock is already taken by the worker 1. So worker 2 has to wait. So now worker process 1, because it finds the status to be available, it updated to matching and then finished the transaction. Now, because process 1 finished the transaction, the lock is released and process number 2 can now get the lock. But when process 2 now reads it, it's already matching. So I could avoid the race condition this way. So this is a pessimistic lock, and I can use it. For optimistic concurrency control, so in theory, what happens is that, let's say, I use the kind of version key, something like this, for status. So it starts from number 1. And now, worker process 1 reads the current status version key, which is 1, and tries to update the driver recode if the status is available with status is equal to matching and where status version key is 1. And also it tries to update the status version key to 2. So with this, status version key is updated to 2 and status is updated to matching. But let's say there is another process who does the same thing. In that case, both of them read the status version key 1 and tries to update the recode with status version key 2. First one succeeds, but the second one fails because the first process updated the status version key to 2, and when the second process tries to update it, it specifies where status version key is 2, so it actually can't find the recode which is to be updated. So in this way, I can avoid the race condition, and the process 2 has to retry now. So this is a basic explanation about the optimistic concurrency control. And in this case, I'll go with the pessimistic lock because okay, so I actually stopped the video and I was thinking for a while, which of this should be better, pessimistic lock or optimistic concurrency control. So now my answer is I will go with the optimistic concurrency control. So the reason is that in the case of Uber system, if the driver's status is let's say if currently the request worker has to wait to get the log of this driver, which means that there is another process who's getting the log, and which means that now that earlier process, worker process, changes the status to matching, which means that even if the second request worker process gets the log of this status, it's not available anymore. It's matching. So that's a kind of thing I have to take care, because in pessimistic lock, the worker process will be waiting for the worker processes are waiting in the queue to get this row's lock. But even if it gets the lock, it's already in the matching process, which means that there's no point waiting in the waiting to get the raw rock. So I use the optimistic concurrency control. So with this, if it fails to get the rock, because the other process has just updated the rock, now this request worker can try with another driver ID. Of course, it is possible that the the driver who was currently matching may reject and come back to available, so it worth retrying later. But yeah, for now, the worker process can try with another driver ID. So for this reason, for this characteristic of this system, I go with the optimistic concurrency control. Okay, so that Howard can avoid the race condition about the driver. So the thing is, I already resolved this one. Okay, and for this one, a request is notified up to one driver at a time, because in a design, this worker process keeps checking a single driver's matching. So single user's matching process is handled by only single worker. So this is already met. There's no other worker process which sends a push notification for that request. Okay, and here a driver is given 5 seconds to accept or reject the request. So yeah, the thing is, okay, so for this one, I have to think who changes the status from matching to available back. So of course it is possible that if driver sends a request to reject the request, with that request, ride service can change the matching status to available. It is possible. But the problem is maybe driver doesn't respond. In that case, who updates the status? And maybe the quick idea is maybe request worker can. After 5 seconds, request worker makes a query to change the status from matching to available. But there's a problem here. If this request worker dies and goes down, there's no one who changes the matching status to available. So yeah, instead of this, I kind of create another column here. Let's say this is matching until. So this matching until is updated when status is updated to matching. And this matching status is set with current time plus 5 seconds. So I can say the driver is in the matching status if driver status is matching and current time is before matching until. So with this matching until column, even if the request worker request worker doesn't have to flip back the status from matching the variable. And also with the answer request with reject, even with that, ride service doesn't have to, change the status from matching to available back. So this is the kind of idea I can use. Okay. And actually, with this, because matching until is incremental, I don't need the version key anymore. So I can use this as version key. So this is it. Okay, so with this, I can say now I meet these three function requirements and also this non-function requirement. Because as I said, oh, okay, so yeah. Okay, I will quickly review the process of the matching. So when user makes a request, the request is pushed into the change data capture. Sorry, pushed into the queue as a change data capture, and this request worker now, consumes the message, and this worker is responsible for matching that request ID, that request. So it keeps trying. So firstly, it reads the driver IDs from the database who are nearby the user who requested. Of course, it is possible that within 1 minute, for that 1 minute, driver moves around. But even with that, driver only moves at max 1 minute distance. So he can come back to the same place within 1 minute. So I think, the driver moves, but I don't have to take care of that too much. So now request worker has 30 drivers who are nearby the user. So he tries one by one. But to make sure that only one request worker sends the notification to the driver, I created the status column in the driver table. So it has offline available matching matched with matching until timestamp. So this request worker does the optimistic concurrency control to when it tries to get the lock of the driver. Yeah. And now, if it can get the lock, and it can update the status of matching, now request worker pushes the notification to the driver through notification service. And now driver reject or accepts the request. Yeah. And now this write service updates the driver status maybe, and it doesn't have to actually. So as I said, it creates the driver response recode, and if it is accept, it creates the match recode and also updates the request status to matched in the single transaction for that Misty. Okay, so these are the process how the user is matched with driver. Okay, so now we're talking about the second topic, geospatial search. So I actually already talked about the geospatial search, geospatial indexes in another video, but I will talk about them quickly in this Uber scenario. So geospatial search, I will be clear how this is used in the system first. So as I said, request worker tries to fetch 30 nearby drivers from the user's location. So I put longitude, latitude here, so the first three request worker can know the longitude, latitude of the user, and now it makes another query to get the nearby drivers. Yeah. So the problem is how I can make this work. So one quick idea is using a kind of composite index on longitude and latitude, but it doesn't work because with the composite index, the database creates the B tree with the tuple longitude latitude, which means that the pointer is sorted by the longitude, but within the same longitude value, they are sorted in the latitude then. But because longitude has the kind of range, so even, after database engine filters the data point with longitude, it cannot filter with latitude in kind of binary search way. It has to scan all the data point with that range. So yeah, in the worst case, if there are so many users, so many drivers in the given longitude range, it has to scan all the point to check if latitude is in the specific range. So this is why composite index doesn't work. Now I can say I will use a specialized geospatial index for this search. So because I put this data in PostgreSQL, what I can think of first is creating the point type. So there is a point type column in PostgreSQL, so I can use it. And the good thing is this point type can create the index, specialized index with this longitude, latitude, with R3. So I will talk about this later. So I can use that R3 index. But one more thing I have to take care is, because if I do this longitude, latitude is just like the XY in the plane. So it doesn't take the cover of the Earth into the consideration. So to consider the Earth, cover of the Earth, I have to use the PostGIS extension. So with this PostGIS extension, I can create a special index with point type, considering the cover of the Earth. So with this, now query for longitude, latitude range is much optimized. So this is the first option. Use the PostGIS extension and create the geolocation index, which internally uses R3. So now I will talk about what the R3 is. So I use this picture. So let's say I will use this one. So R3 is a kind of tree structure. So internally, the point are stored in this kind of tree structure. So firstly, I would say the point exists only in the gray area. So there are no point in the white area. So if there's a point, a kind of cluster of the point, it creates the minimum boundary box. It thinks of the minimum boundary box and creates a node which corresponds to that minimum boundary box. So in this case, A corresponds to this, B is this one. And then it creates the parent box, which is the minimum boundary box of these two or maybe multiple minimum boundary boxes. And it does recursively. So I can say the tree is constructed in a bottom-up approach, recursively. So in this way, the tree structure becomes like this. So let's say I'd like to search for the area around here, close to B and H. Firstly, it takes a look at T and U, and it can say, database engine knows the longitude, latitude range of the search area. It can immediately say if specific box has the overlap or not. So in this case, either T and U has each of T and U has the overlap with the search area. So it doesn't trim. And then for T, it goes down and check NPQ. I can say P doesn't have the overlap and Q doesn't have the overlap quickly from the longitude latitude range check. So the database engine now trims N and P, and it only checks, it trims P and Q and only checks N. And it goes down, and for A and B, A can be trimmed, so now it checks all the point in B. And the same thing happens from U. From U, it goes down and trims Q and S, trims S, and it goes down to R, and now H-A-I-J, it trims I and J and checks the point in H. So this is how R tree works. So the good thing is, unlike the composite index, what I checked is box B and H. So the number of points to be linear scanned is quite limited now. So this is good. And also, when this minimum boundary box is created, tree structure is created, database engine makes it the balance tree. So if there are many boxes in the specific area, the parent should have many child boxes, and in that way the tree is balanced. So the query performance of the read query is stable. So that's another point. But the problem is, when the point moves frequently to the long distance, it happens for many points, the tree structure has to be tree structure has to be restructured. So that's the weak point of this R tree. And in case of Uber, driver moves around, and it's quite fast because they're on the cars. So the restructure of the tree is quite frequent, which makes the update query slow. So in case of Uber, R tree is not the perfect option. That being said, I introduced another geospatial index, which is named GeoHash. So with GeoHash, it works in this way. So all the area is divided into 4 rectangles, so recursively. And as you can see from this example, each tile, I should say, unit has the same size. Yeah. And every time it divides the area into 4, it adds the suffix 0, 1, 2, 3. So 1, 3 becomes 130 to 133. So I call this number of the minimum tile, unit tile, as the GeoHash of this area. So internally, GeoHash stores the longitude, latitude, and the GeoHash as another column. So the good thing is, let's say the system would like to search this area, 0 to 1. So the point to be checked is only the point whose hash value is 0 to 1. Or if the search area is on the boundary, maybe 0032 and 0122, maybe 0302. But anyway, the tiles to be scanned. Tiles whose point to be scanned is limited. So that's the point. And this GeoHash internally creates the B tree of the hash value, which means that the database engine can find the first point in this tile in log n time, and then it linear scans the point in this 0, 1, 3 tile. So this is good in terms of the let's say, firstly I can say number of tiles. Sorry, I should say, let's say I try to search this area, it has to check only 0, 1, 2 tile and 0, 3, 0 tile. So the number of points to be linear scanned is limited, even though there is a kind of boundary problem. Yeah, and that being said, for Uber, this is better because when the driver moves around and if the point position is updated, all it has to do is recalculate the hash value and update the hash value in the column for that row. So this is quite, fast for the update queries. So now I say for this Uber system, I should use a geohash. And geohash basically comes with Redis, for example. So I use Redis here. So instead of putting the user's longitude, latitude here and using PostGIS here, I put longitude, latitude to user ID mapping in this Redis geohash. So it has now Regensburger reads the point from this. Yeah. And update location query should go to this Redis geohash. I will talk about this later, but this is good in terms of the performance of the database too. Because in case of Uber, the driver's location has to be quite accurate. So even if driver moves for 3 seconds, 5 seconds, the location should be updated for each driver, which overloads the PostgreSQL database. So it's a good idea that I separate the database and use the Redis, because Redis is in-memory database, so it performs much better than PostgreSQL in terms of the throughput. So now location service sends the update location query to Redis, and Redis updates the point data. Okay. So this is about the geospatial search, but I have one more thing to be added. So this geohash uses a tile whose shape is rectangular. So again, considering the cover of the earth, rectangular tile is not the best. So Google developed S2, which geolocation. And with this S2, each tile looks like this shape. Yeah. Smaller one looks rectangular, but not strictly, I guess. And for larger one, obviously this is not the rectangle. So this is a kind of optimization considering the curve of the earth. Yeah, which is used in S2 index. Or Uber actually developed internally the geolocation index named H3. H means hexagon, and the word is divided into rectangles, and each hexagon has a child hexagon recursively. So this is H3. So because I'm developing the Uber system, I would go with the H3. So Redis has the H3 index internally, so I can use it. Okay, so this is the geospatial search. Good. Okay. That being said, I finished my today's system design practice. Tomorrow I will talk about the scalability. Okay, thank you. Bye.